Welcome to our exploration of number systems, the foundation of data representation in computing. Every piece of information processed by a computer, from text to images, is ultimately represented as numbers, but not all number systems are the same. In this video, we'll break down what number systems are, why they matter, and how they form the backbone of digital technology. By the end, you'll understand how computers interpret and manipulate data using different number systems. Let's begin our journey into the world of numbers and see how they power everything digital around us. A number system is essentially a way to represent numbers using a consistent set of symbols and rules. In our daily lives, we use the decimal system, which is based on 10 digits from 0 to 9. However, computers use other systems, such as binary and hexadecimal, to process and store data efficiently. Each number system has its own base or radix, which determines how many unique digits it uses. Understanding these systems is key to grasping how computers handle everything from calculations to memory storage. The decimal system, also known as base 10, is the most familiar number system to us. It uses 10 digits from 0 to 9, and each position in a number represents a power of 10. For example, in the number 345, the 3 stands for 3 hundreds, the 4 for 4 tens, and the 5 for 5 ones. This positional value system makes it easy to represent large numbers efficiently. Understanding the decimal system is crucial because it serves as a reference point for learning other number systems. The binary system, or base 2, is the language of computers. It uses only 2 digits, 0 and 1. Each position in a binary number represents a power of 2. For instance, the binary number 1011 equals 1 ems ut plus 0 ems fa plus 1 ems ta plus 1 ems 1, which is 11 in decimal. Computers use binary because electronic circuits have two states, on and off, making binary a natural fit for digital technology. Mastering binary is essential for understanding how computers store and process information. The octal system, or base 8, uses 8 digits, 0 through 7. Each position in an octal number represents a power of 8. For example, the octal number 157 equals 1 ems 60 fa plus 5 ems ut plus 7 ems 1, which is 111 in decimal. Octal was once popular in early computing because it's easier to convert between binary and octal than between binary and decimal. While not as common today, understanding octal helps in grasping the evolution of number systems in computing. The hexadecimal system, or base 16, uses 16 symbols, 0, 9 and AF, where A stands for 10 and F for 15. Each position in a hexadecimal number represents a power of 16. For example, the hex number 2F equals 2 times 16 plus 15 times 1, which is 47 in decimal. Hexadecimal is widely used in programming and digital electronics because it's more compact than binary and easier for humans to read. It's especially useful for representing memory addresses and color codes. You might wonder why we need so many number systems. Each system serves a unique purpose. Binary is perfect for computers, octal and hexadecimal make binary easier for humans to read, and decimal is what we use daily. These systems allow us to bridge the gap between human understanding and machine processing, making data representation efficient and practical in different contexts. A key feature of all these number systems is positional value. The value of each digit depends on its position in the number and the base of the system. For example, in the decimal number 345, the 4 is worth 40 because it's in the tens place. In binary, the same logic applies but with powers of 2. This concept is what makes number systems powerful and flexible for representing any quantity. Let's see how to convert a binary number to decimal. Take the binary number 1101. Starting from the right, each digit is multiplied by 2 raised to the power of its position. So 1 times 2 3 plus 1 times 2 2 plus 1 times 2 0 equals 8 plus 4 plus 0 plus 1, which totals 13. This method works for any binary number, making it easy to translate between systems. To convert a decimal number to binary, repeatedly divide the number by 2 and record the remainders. For example, to convert 13 to binary, divide 13 by 2 to get 6 remainder 1, then 6 by 2 to get 3 remainder 0, and so on until you reach 0. Reading the remainders from bottom to top gives you the binary number 1101. This process is systematic and can be applied to any decimal number. Converting binary to hexadecimal is straightforward because 16 is a power of 2. Group the binary digits into sets of 4 starting from the right. Each group translates directly to a hexadecimal digit. For example, the binary number 11,011,110 becomes 1101D and 1110E, so the hex value is DE. This method simplifies reading and writing long binary numbers. To convert hexadecimal to binary, simply replace each hex digit with its 4-bit binary equivalent. For example, the hex number 2F becomes 10 for 2 and 1111 for F, resulting in the binary number 101,111. This direct mapping makes conversions quick and error-free, which is why hexadecimal is so popular in computing. Octal and binary conversions are also simple because 8 is a power of 2. Group binary digits into sets of 3, starting from the right, and convert each group to its octal equivalent. For example, binary 101,110 becomes 101,5 and 110,6, so the octal value is 56. This method is handy for interpreting binary data in a more compact form. Computers use binary because their hardware is built on switches that are either on or off, representing 1 or 0. This makes binary the most reliable and efficient way for computers to process and store data. Every operation, from arithmetic to logic, is ultimately performed in binary, making it the universal language of computers. All data in computers, whether numbers, text, images, or sound, is ultimately represented as binary numbers. For example, the letter A is stored as 1,000,001 in binary. This consistent representation allows computers to process diverse types of information using the same basic principles. Understanding this is key to grasping how computers work at a fundamental level. In computing, numbers can be signed or unsigned. Unsigned numbers represent only positive values, while signed numbers can be positive or negative. The most common method for representing signed numbers is 2's complement, which makes arithmetic operations straightforward for computers. Understanding this distinction is important for interpreting data correctly. 2's complement is a method for representing negative numbers in binary. To find the 2's complement of a number, invert all the bits and add 1. For example, the 2's complement of 101,5 is 11,111,011, which represents. This system simplifies subtraction and other arithmetic operations, making it the standard for signed numbers in computers. Floating point numbers are used to represent real numbers, including fractions and very large or small values. They use a format similar to scientific notation, with a sign, exponent, and mantissa. This allows computers to handle a wide range of values efficiently, but also introduces some limitations in precision. Floating point representation is essential for scientific and engineering calculations. Characters like letters and symbols are represented in computers using encoding schemes such as ASCII and Unicode. Each character is assigned a unique binary code. For example, the letter A is 65 in ASCII or 1,000,001 in binary. Unicode extends this to cover characters from all languages, making computers truly global. Besides numbers and characters, computers also represent data types like images, audio, and video. These are broken down into binary data using various encoding methods. For instance, images are stored as pixels with binary color values, and audio as sequences of binary samples. Understanding these representations helps in fields like multimedia and data science. In summary, number systems are the foundation of data representation in computers. From binary to hexadecimal, each system plays a vital role in how information is stored, processed, and understood. Mastering these concepts opens the door to deeper understanding of computing and technology. Whether you're a student, programmer, or just curious, knowing how data is represented is a valuable skill in the digital age.